So I'm Afroditi Grigoropoulou from Greece, and I will show a random forest model used to actually build a species distribution model for a genus of an insect, which is a mayfly. So in our group, Sami, who is our supervisor, has been contacting many researchers across the world since 2015, and he has been asking for data from aquatic insect samplings globally, because he had this idea to assess the global patterns of their biodiversity. And we're interested especially in aquatic insects because they lay their eggs. So aquatic insects are like dragonflies and 3 other orders that nobody knows. And they lay their eggs in the river. And different genera or species have different kinds of sensitivities to water pollution. So the presence or absence of particular genera are used in biomonitoring and conservation planning. So that's why we want to track their biodiversity. So now we have this database under review, which includes some million occurrence points of different genera of insects. And I will use data from this database to build species distribution model. And the original idea was to build one model per genus to predict its genus's distribution. We will talk about this in the end. Yeah, so I will show you, this is the genus which I will use, super beautiful. I will show more the pre-processing of the data. That means the steps going from the tables that Chaim created to the modeling part. If it's super repetitive, tell me.
So what's SDM?
Sorry?
What's SDM?
Sorry, it's species distribution modeling.
Okay.
So the point with the random forest here is to classify each modeling unit, that is a subcatchment, into 1 or 0. That means presence or absence of the species. And you also have the option to predict the probability of each occurrence. So basically, we're talking about habitat suitability. So how suitable is the environment in its subcatchment to host this genus? Yeah, so the species data look like that. Now they look ugly, but basically I have the genus name, longitude, its coordinates, and I have also previously extracted the subcatchment ID where the genus occurs. I did this with GDAL location info, which is my favorite function. So I have the subcatchment ID for each point, and then the drainage basin ID, and the computational unit ID, which is these tiles from the irregular tiling system that Chaim showed. So yeah, first I define in which computational unit the genus occurs, which is, where is it? Here. Which is this red polygon in Colombia, going down here. And these are the points, which are 100. So these are 100 points, but they're overlapping. Because maybe they belong to the same subcatchment, but they're taken in different years, which is a problem because we end up with 11 samples instead of 100. And then from the computational unit, we will get the single basin, which is the Magdalena River basin. So if we zoom in this basin, we reach to the level of the subcatchments. So you can see that in reality, it's very few points to work with machine learning, at least with this approach. But I will go Yeah, so this is what the table for the statistics of one biplane predictor looks like. This is what Jaime computed with the mean, max, range, mean, and standard deviation. And now I have to extract the rows based on the subcatchment ID. And I'm doing this using grep because R collapsed. And where is it? Sorry, let's keep this. Yes, here. So for each bioclim variable, I do grep and I get a table. And all these bus variables are just for reproducibility because I was supposed to do this for 1700 genera and for all the basins, for all the computational units. And I would do it in parallel. So I would send each job to another core. But then I decided that I can do it in xargs and overcome my fear with xargs. So I printed all the variables in a file, and I used this syntax using what is P? Yeah, processor, and giving the bioclim variable as an argument. So one argument, 5 processors, and it worked. I'm really happy for that. What's that? Yeah, this is just to check that the output of its extraction is correct. So it has the same word count. Then I basically do the same for the land cover variable and inserting some headers. Yeah, and then we have the tables of the stream order, which are not they're not the same. So the column names change orders. It's not just min, max, min, etc. So I needed to grep based on the column name, which was a little bit more complex because I needed to use oak. Where is it? Here, this line. Really ugly. Anyway, and basically I do the same in xargs. Yeah. And then to join the predictors, I just used R because I reached the point where the data was, so R could handle it. I will skip it. I will show you the final table. Yeah, so we reached the point that for the whole basin, we have the subcatchment ID and all the predictors that I will use for the models. But now we need to extract the subcatchments where the genus occurs and 10,000 random subcatchments that I will use as pseudo-absences in the species distribution model for the classification. So again, I work with the subcatchment IDs. And for the random pseudo-absences, I use this line. So with the file, you do this shuffle and you get 10,000 random samples. Yeah. And I think, so then the last step of the modeling will be to predict on the subcatchment. So I needed to crop the to predict on the basin. So I needed to crop the computational unit file to the basin. And I did this in Grass. First, I loaded the computational unit tile. What's that? The subcatchment. Yeah, the computational unit. And this is the basin file, which I will use as a mask. And now with our map calc, you calculate basically, how can I describe this? You calculate based on the mask, the area that you want to crop out. And with a zoom, you zoom to the area. So yeah, I exported the file that I will show you in the end. And now the random forest. So yeah, I read the presences. I read in the pseudo absences file. I add a column with presence or absence, 1 or 0 for the classification. Then I scale back some predictors because the raster files are multiplied by a large value so that the values are integers. So I convert them back to float. Here. And now there comes the question whether I should split the data into train and test. Because in random forest, I've read that there's no need to split the data because in each bug, this is done automatically. But then Giuseppe said to me that the reviewers always ask for splitting into train and test. I didn't do it in this case because we are not reviewers. So I use the whole data. And I use the range package, which is a faster implementation of random forest. I had done some tuning for another project, so I used these parameters. I'm not showing the tuning. Yeah, there's another thing. So I had 11 cases of presence, but 10,000 pseudo absences. And there had to be so many in order to cover the whole environmental range. But this causes class imbalance in the model. So to overcome this, in each bug, I use the subsample of the data. So equal pseudo absences with the presences. So in each bug, it chooses 11 absences and 11 presences. But I'm not convinced yet. The out-of-bug score is better this way than if you, yeah.
So Ranger does exactly the same thing that random forest does?
Yeah, yeah.
The name of the bug.
Yeah.
It's just it's random forest plus that.
Yes. Yeah. But they have some differences in variable importance. Like with exactly the same parameter, they give a different variable importance.
Yeah,
Because they use the Gini.
Yeah, they could implement a slightly different variable imports. But anyway, the most important, they should be maybe changing a bit, but they should be there. I mean, they're top.
Yeah, yeah.
Important.
Okay. Yeah, so I did this thing with the subsampling. And this is the output of the model. So for random forest, for the classification in random forest, the only error that you get, like score that you get, is the out-of-bug error, from what I have understood, which changed in each run. So it goes from 9 to 12. I think it's just random results because the data is not so good.
Yeah, also, yeah, this is due to the low number of presents.
It should be close to 1, this value.
The error. So an error of this is based on this matrix. Yeah. So,
Close to 0.
but then if it's close to 0, we have overfitting, right?
It should be.
Yeah,
Yeah.
okay, so it's good performance.
Good
would be
performance,
something
yeah.
close to 0.
Close
Yeah.
to 0. Yeah.
So that,
Yeah, it's 9%. But if you look at the matrix, I mean, the samples are
yeah.
very, very few. Then I made the variable importance plot. And the most important variable was the mean of the flow accumulation. And this is normal because also we don't know if the samples that we have are adult insects or larvae. that are in the river. So if they're larvae, this makes sense. Then it was the standard deviation, the Strahler stream order. But I really don't know if I can interpret this variable importance. Longzhu once said that random forest is good for predicting, but not for interpreting. I'm quoting Longzhu.
Yeah, I mean, because it's complex in terms of the function, but
Yeah.
that's why you get the variable importance to try to explain it more.
In any case, this variable importance that we're getting at this point is basically which variables matter the most to predict as zero, right?
Which variables? Sorry.
Which variables import the most important, right? For each predict as zero, right? It's like no presence of an insect, which in reality what's the opposite.
But why?
Because we want to see which variables are conditioning the presence of a.
No. Why? I mean, why do I see which condition the absence?
Right.
Why is only conditioning the absence? It's zero?
Yeah.
Because there are too many. There are
Yeah, because we barely have data of the presence of the insect.
Yeah, again, the unbalanced problem.
Mm.
With 7 samples, you cannot abstract any rationale of the presence of the
Mm.
This is what we mentioned.
Yeah.
Another question.
Yeah.
I don't know. It's not, there are not too much explanatory variables corresponding to the observations. Is it affecting something? Or you can have 11 observations and 30 variables that explains the variability of these 11 observations. Or
Yeah.
each explanatory variable will change in each observation.
Yeah, that's why we say that the sample is very
Yeah.
small. Good to get something really valuable. Something very important. Yeah. But if you pick up other species, they have more. Why you pick up the one?
Because it was because
the most challenging one. Okay.
no, because the whole distribution was in a single basin,
Ah, okay.
and I didn't want to show all the parallel stuff,
Ah,
etc.
okay. Cool.
It's for educating reasons.
Cool.
Yeah, so then with this great model, I make a prediction on the raster, and no, I predict basically on the tables that have all the subcatchments. Yeah, I didn't change it. So this would be the case if my prediction was 0 or 1, but in the end I chose the probability prediction. So this is a probability. And based on this table, I made a file with reclassification rules to reclassify the raster with the basins in grass, because in R I couldn't do it.
Sorry, can you repeat this step?
Yeah.
You get to it?
I wanted to reclassify the subcatchments based on the probability of the insect occurrence.
Okay.
So I made a reclassification file for grass,
Okay.
which is basically like this, but modified. And then in grass, I imported the file of the basin with the subcatchments, and I reclassified it based on the rules. I exported it, and it looks like that. Then I read that this species occurs at high elevations, and this overlaps with the elevation map. So I can't really say that I trust the map, but it's not too bad. That's all.
I have some knowledge about migration of like species. One sample of this species here, and then based on my knowledge about the dynamics of that species, I say like there is a Gaussian probability that's centered on that place that I'm gonna find more samples of that same species that there, because that's really by a lot like you're the best of aggregating the data.
Yeah, but the thing is that it's not a rhino. It's an insect occurring only in Colombia, not even a dragonfly. I mean, it's not well studied. And one might be, but I need to do it for the global.
You know, we she's dealing with this dragonfly they fly. So you can maybe easily say, okay, they are fast flyers. So
The
can
dragonflies,
say-
yes. This one, no.
this one, no.
No.
But you can generalize, okay, let's suppose that they are flying 200 meters. And then, of course, you get also the value of the 200-meter round, so you get another 3-4 pixels, 9 pixels total. So you can increase the number of observation in this way. So you can, another way is also, but it's not her case, they use it as a predictor also. So you have as a predictor over here, and there are different techniques to use it. They have the so-called expert range map. So an entomologist, they say, okay, these are the point. Yes, it's true. I was also there, and I think it's going to be also here, and they draw manually the map. Okay, and this suitability expert knowledge suitability map, yes, the expert knowledge maps. Usually they have a very broad range of like 1 degree, 100 kilometers. They can be used for 100 kilometers on off, you know. So as they give you a sense, but at least you know you avoid to have this kind of over here high predictability, because here you don't have. But this is something for big, for large big animal, elephant, lion, they have this kind of. But to small insect, nobody knows.
Yeah.
Okay. Very
Yeah.
good. So you develop some. Now is the tool to switch also in Python.
Yeah. So yesterday we had a nice brainstorming session
Okay.
where they suggested basically to build just one model and not 700, which will include all the species. And it's very complicated for me to explain it. So the output would be basically in each pixel a probability that each species occurs. And this would be done with a neuronal network. Maybe I will show it next year.
Okay. Good. And on this, I want to add in also that there is this new library, machine learning R3.org, that actually is very okay. I don't know why machine learning, maybe R machine learning.
Is it in R and Python?
So it's in R, but actually they have the same concept. It's like, can anyone Google it? Maybe I lost internet. Here. Because there is stuff. Okay, machine learning R3. So it's very, I think it could be that it's Python derived also because they have the same flagging and actually I was implementing in one of my last model. It's much faster, a bit more complex. It's more close to the Python syntax than not to the. And they have all the different neural network, random forest, and so on. So it's quite particular to using this aspect. Okay. Any other question? Okay, good. Thank you very much for